Probability and queuing theory. Case study. Joint distribution. The joint probability distribution can be expressed either in terms of a joint cumulative distribution functions or in terms of a joint probability density functions or joint probability mass function. These in turn can be used to find two other types of distributions: the mathematical distribution giving the probabilities for any one of the variables with no reference to any specific ranges of values for the other variables, and the conditional probability distribution giving the probabilities for any subset of the variables conditional on particular values of the remaining variables. Diagrammatic representation. Many sample observations are shown from a joint probability distribution. The marginal densities are shown as well, that are defined on the probability. The joint probability distribution for is a probability distribution that gives the probability that each of falls in any particular range or discrete set of values specified for the variable. In the case of only two random variables, this is called a bivariate distribution, but the concept generalizes to any number of random variables, giving a multivariate distribution. These probabilities are the joint distribution in any one cell. The probability of a particular combination occurring, the product of the probability of the specified result for A and the probability of the specified result for B. The probabilities in these four cells sum to 1, as it is always true for probability distributions. Moreover, the final row and the final column give the probability distribution for A and the marginal probability distribution for B respectively. For example, for A, the first of these cells gives the sum of probabilities for a being regardless of which possibility for B in the column above the cell occurs as 2 by 3, thus the marginal probability distribution. Consider the flip of the two fair coins. Let and be discrete random variables associated with the outcomes of the first and second coin flips respectively. Each coin flip is a Bernoulli trial and has a Bernoulli distribution. If a coin displays heads, then the associated random variable takes the value 1 and it takes the value 0 otherwise. The probability of each of these outcomes is 1 by 2, so the marginal density functions are the joint probability mass function of and defines probabilities for each pair of outcomes, all possible outcomes. Since each outcome is equally likely, the joint probability mass function becomes. Since the coin flips are independent, the joint probability mass function is the product of the marginals. Consider the role of a fair die and let if the number is even, that is 2, 4 or 6, and otherwise furthermore let if the number is prime, that is 2, 3 or 5, and otherwise the diagrammatic representation. Then the joint distribution and expressed as a probability mass function is these probabilities necessarily sum to 1, since the probability of some combination of occurring is 1. Consider a production facility that fills plastic bottles with laundry detergent. The weight of each bottle of Y and the volume of laundry detergent is contains X are measured. If more than one random variable is defined in a random experiment, it is important to distinguish between the joint probability distribution of X and Y and the probability distribution of each variable individually. The individual probability distribution of a random variable is referred to as its marginal probability distribution. In general, the marginal probability distribution of X can be determined from the joint probability distribution of X and other random variables. If the joint probability density function of random variable X and Y is the marginal probability density function of X and Y, which defines is given by, where the first integral is over all points in the range of X, Y, for which X equal to small x, and second integral is over all points in the range of X, Y, for which Y equal to small y. Joint cumulative distribution for a pair of random variables. The joint cumulative distribution function of CDF is given by that the random variable takes on a value less than or equal. Thank you.